Good morning, and welcome to the industry session, the first talk, which is going to introduce IQM, one of the major sponsors of this event. The speaker will be Erik Hyppe, who is a quantum engineer at IQM. Please post your questions during the talk to the chat. We will have 3 minutes at the end to answer those. Erik, thanks for joining us today, and please go ahead with your talk. Looking forward.
Thank you for the nice introduction. I'm very excited to be here representing IQM. So as you already heard, my name is Erik Hyppe. I'm a quantum engineer at IQM Quantum Computers, and I'm also a PhD student at Aalto University, where I'm doing my PhD based on my research at IQM. And today I'm actually not going to talk about our core technology, but one of our research projects. And more specifically, I'm going to talk about the Unimon qubit. That is a novel island-free superconducting qubit that we have developed at IQM in collaboration with QCD Labs at Aalto University. And just recently in March, we have published an archive preprint of our paper. So if you find this talk interesting and you want to find more information, you should definitely check our archive preprint out. Okay, so today I'm going to start with a brief introduction to superconducting quantum computing and superconducting qubits. Then I want to explain why we are interested in developing novel qubit types at IQM. After this, I will introduce you to the concept of the Unimon qubit. I will first present the theory of the qubit and explain why it has some quite nice advantages. And then I will show some first experimental results that we have obtained from very first Unimon qubits fabricated at IQM. And finally, I will briefly summarize my talk, and then we have a few minutes for questions, hopefully. Okay, so let's start with this introduction. So as you probably know, superconducting circuits provide one of the leading platforms for realizing a large-scale and useful quantum computer in the future. And the progress with superconducting qubits and circuits has been really rapid during the last few decades, and especially during the past few years. So in 2019, the team of Google Quantum AI demonstrated quantum supremacy in this landmark experiment where they were using their 53-qubit Sycamore processor. Just recently, at the end of last year, the QDev group at ETH Zurich demonstrated a distance-free surface code close to the break-even threshold by using their 17-qubit superconducting quantum processor. But despite of these very impressive results, we still need to scale up the number of qubits and improve the coherence of the qubits and the gate fidelities in order to be able to do some useful computations on our quantum computers, either through these noisy intermediate scale quantum computers or through full-fledged error correction. At IQM, we believe that a good target for the fidelity of the quantum operations is about 99.99%. So how do we actually implement superconducting qubits? Well, superconducting qubits are actually no more complicated than non-linear resonators that can be utilized as effective two-level systems. This non-linearity comes from using Josephson junctions in these circuits, and a Josephson junction consists of two superconducting electrodes that are separated by an insulating layer. The special thing about Josephson junctions is that their potential energy is not a quadratic function of the superconducting phase difference, but actually it has this cosine shape. And this makes it possible to implement nonlinear circuits and also qubits. In principle, you could use just a single Josephson junction as a qubit, which would constitute a charged qubit, but this is not what people do because this would be a very bad qubit. So what people typically do is that they use some additional circuit elements like capacitors or inductors or arrays of Josephson junctions in order to engineer the energy spectrum of the qubit and to modify the susceptibility of the qubit to different common noise sources, such as electric charge or magnetic flux. One important thing to keep in mind is also that because superconducting qubits are actually nonlinear oscillators, you have a large number of energy states, and to do these computations, you typically want to limit yourself to the two lowest energy states. But the higher states still exist, and you can use them to your advantage, for example, in 2-qubit gates, but they also lead to some inevitable errors in your quantum gates. Okay, so what makes a good superconducting qubit then? Well, a good superconducting qubit should be able to preserve its quantum information for a long time, so it should have a high coherence. Then you must be able to implement accurate and fast single and 2-qubit gates, and you should be able to do accurate and fast readout of the quantum state. You also must be able to initialize the qubit into a known state. And it's also very important that you can fabricate the qubit in a reproducible manner, and this becomes more and more important as you scale up your system. And as a result of these criteria, I would say that there are two quite important figures of merit for superconducting qubits, and these are the anharmonicity, that is defined as the frequency difference of the two lowest energy transitions, and a high anharmonicity enables you to do fast gates with a high fidelity and low leakage to these higher non-computational states. The other important figure of merit is coherence, measured by relaxation time and coherence time. And if you have a high coherence, you can do high fidelity quantum gates. So currently, I would say that there is one mainstream superconducting qubit, that is the Transmon, and then there is the fluxonium that seems to be emerging as a serious competitor to the Transmon. So the Transmon is a Josephson junction that has been shunted by a large geometric capacitance. And the benefit of the Transmon is that this capacitive shunt significantly reduces the sensitivity of the qubit to charge noise. And this is one of the reasons why you can have high relaxation and coherence times of even up to half of a millisecond with Transmons. In addition, people now routinely realize high fidelity single and 2-qubit gates with Transmons, and the control of Transmons is relatively easy because they have large matrix elements. Also, the circuit is very simple, and you can fabricate it in a reproducible manner. The major disadvantage of Transmons is that it has only a low anharmonicity of about 200 megahertz, which corresponds to about a few % of the qubit frequency. And this is problematic if you want to do some fast operations, because then your qubit can end up into the second excited state, which is a non-computational state, and this is very harmful, especially if you want to do quantum error correction. Well, when it comes to a fluxonium, it is based on a Josephson junction that has been shunted by a superinductance. These superinductances can be implemented in a variety of ways, but typically people use an array of large Josephson junctions to act as an effective superinductance. The benefits of the fluxonium include that you can really have a very high coherence time of about a millisecond even, and you can have a high anharmonicity of several gigahertz. And these properties in combined enable you to do very high fidelity quantum gates. But the fluxonium also has its own problems. So these conventional fluxonium qubits can have a low qubit frequency, and this means that you will have a high thermal population, and then you will need some reset protocols to reset your qubit state, and you may also need some special techniques for implementing single qubit or 2-qubit gates. Then these junction arrays can come with some parasitic capacitances, and you also typically have a lower single-shot readout fidelity as with the Transmon. Okay, so if we have these nice qubit types already, so why do we then want to study some new types of qubits? Well, the computational power of the current quantum computers is still severely limited by these errors in the single and 2-qubit gates. And these gate errors can be caused by multiple factors. For example, leakage to the non-computational states, decoherence or crosstalk or some residual interactions. And there are obviously multiple solutions to reduce these gate errors. So for example, you could use some novel pulse shapes for your gates, or you could use some novel coupling schemes, or even like try to engineer better electronics with some lower noise. And one good way to try to improve these error or try to reduce these gate errors is to design novel qubit types that would be insensitive or more resilient against some of these common error sources. And that is why we have designed the Unimon. Okay, so let me then introduce you to the Unimon. And I will first go through the theory, and I will begin by summarizing the advantages of the qubit, and then I will explain the theoretical background behind these advantages. Okay, so the Unimon has a high anharmonicity as compared with Transmon qubits. It is also fully protected from low frequency charge noise and well protected against magnetic flux noise, which should enable a high coherence. Then the structure of the Unimon is very simple because the qubit only incorporates a single Josephson junction in a gradiometric resonator. And also the circuit contains only ordinary geometric inductors, and you do not need any superinductors or junction arrays and therefore you do not need to worry, for example, about these parasitic capacitances. Here I'm showing a circuit model that can be used to approximate many common superconducting qubit types. And the important thing is that the values of the energy scales pretty much determine what type of a qubit you have. So here in the lower figure, I'm showing you a map of common superconducting qubit types based on these ratios of the energy scales. The transmon is located here on the y-axis because it has no inductance. The fluxoniums, shown with green color, have a small inductive energy because they have this huge superinductance. And the Unimon is located in this new regime where you have a quite high inductive energy because you are only using an ordinary geometric inductor. And even more importantly, the Unimon has an almost equal Josephson energy and an inductive energy, which makes it possible for us to implement a high anharmonicity despite of having a quite high capacitance and a low inductance. So how do we implement the Unimon? Well, the Unimon is based on a grounded coplanar waveguide resonator that incorporates a single Josephson junction in its center conductor. And this Josephson junction is a nonlinear circuit element, as I have explained, and this converts some of the normal modes of this resonator system into anharmonic oscillators. And then you can use one of them as a qubit. And what we have done so far is that we have used the lowest frequency mode as the qubit because it has the highest anharmonicity. So here in this figure, I'm showing you a schematic illustration of the Unimon where blue color denotes superconducting material. And I'm also showing you the voltage profiles of the qubit mode for two different values of the flux bias. And you can see that we can modify the voltage profiles with the external flux, and this makes it possible to also tune the frequency of the qubit. Now I will very briefly try to explain how do we model this circuit, which is actually not very trivial because it is distributed in its nature, unlike many other superconducting qubits that you can describe easily with a lumped element model. Well, to start with, we use the circuit model here, and then we take the following steps. So we first solve the classical normal modes of this circuit, and we do this by approximating the phase bias Josephson junction as a linear inductor. And this is a bit similar to what was done in this nice theory paper by Burassa et al. From 2012, but we have extended theory to also incorporate these external magnetic fluxes. Then we make a single mode approximation because at the end, we are only interested in one of the modes that we will use as a qubit. And finally, we quantize the obtained classical Hamiltonian by enforcing the canonical commutation relation between the charge and phase variables. As the final result, we obtain the Hamiltonian shown here. And so you can see that it resembles the Hamiltonian of a fluxonium somewhat, but it's also good to note that, for example, these capacitive and inductive energies are actually functions of flux, as I'm showing here, because the circuit is distributed. Now I want to explain why this circuit is protected against low-frequency charge noise. So this is based on the fact that the Josephson junction in the circuit is inductively shunted by the center conductor. And this means that the potential energy of the Unimon is a non-periodic function of the superconducting phase, as I'm illustrating here. And as a result, you can show in theory that the Hamiltonian is independent of any DC offset charge, and this gives us the insensitivity against charge noise. In comparison, for example, in transmon, you have this periodic potential, which means that you will be sensitive to charge noise, at least to low frequency charge noise, at least to some extent, especially when it comes to the higher energy states. It's also good to note that we use an actual geometric inductor to provide the inductive shunt instead of an effective junction array-based inductor. And this truly means that we should be fully protected against this low frequency charge noise, and it should also make it easier to target some specific or to target the parameter values in a reproducible manner. When it comes to the flux noise protection, there are two factors that contribute to it. So firstly, we have designed the circuit such that it is gradiometric. So this means that the qubit is only sensitive to the difference of the external fluxes through these two loops. And so what this means is that if you would apply a homogeneous magnetic field, and then you would increase the field strength, you would actually not affect the qubit mode at all. So you need an inhomogeneous magnetic field, and this means that you will have some protection against external magnetic fluxes. The other thing that protects the qubit from flux noise is that we have a flux-insensitive sweet spot when we use a certain flux bias. At the sweet spot, the frequency of the qubit is first order insensitive to the applied flux, which provides additional protection against magnetic flux noise. As the final theory remark, I want to try to explain you why we can have a high anharmonicity without using any superinductors and despite of having a quite high capacitance in our circuit. So this is based on the fact that we have designed the Unimon to have a Josephson energy that is close to the inductive energy. And as a result, when you look at the Hamiltonian of the qubit at the sweet spot, you can see that the quadratic potential energies owing to the inductor and to the Josephson junction are almost fully cancelled. And this means that the importance of the higher order terms is increased, and as a result, the anharmonicity is increased. Here I'm trying to illustrate this cancellation effect, where I'm showing you this cancellation of the cosine and the quadratic potential, and as a result, you obtain this highly non-quadratic potential. And here below, I'm also showing you a theoretical prediction of the anharmonicity of the qubit as a function of the flux bias, and you can see that at this optimal half-flux quantum operating point, the anharmonicity is greatly increased. And I would like to point out that this cancellation effect has some similarities to the quantum qubit that was introduced by Will Oliver's group a few years back. But the important difference to the Unimon is that we are using a geometric inductance instead of a short junction array, which gives us this full low frequency charge noise protection as I've described earlier. Okay, so let's then move on to the experimental results that we have obtained so far. So to study the Unimon experimentally, we fabricated some single Unimon qubit samples, each of which consisted of 3 Unimon qubits. And so in this false color microscope image, I'm showing the Unimons with the blue color. And each of the Unimons was capacitively coupled to a readout resonator shown with red, which made it possible to use dispersive readout for the qubit state measurement. Also, each of the qubits was capacitively coupled to its own drive line that I'm showing with green color. And this made it possible to drive single qubit gates. And then we also had this readout line for reading out the qubit state, and also an external coil to control the flux difference through the qubits. I would like to point out that the coplanar waveguide structures of the Unimons were designed to have a characteristic impedance of about 100 ohms, and this really stresses the fact that you do not need any superinductors. And in the following slides, I'm showing the results for the 5 Unimon qubits that we have characterized to date. So let's begin with something quite simple. And so here I'm showing you the resonator response, the readout resonator response for one of the qubits in a so-called resonator spectroscopy experiment, in which we are sweeping the frequency sent to the readout transmission line and also sweeping the external flux bias. And so we can see here that the frequency of the resonator changes periodically in the applied flux, and this is expected for a superconducting system. And so this frequency of the resonator is changing because the qubit frequency is changing, and it is pushing the frequency of the resonator. We can also see that we have these avoided crossings from which we can determine the coupling between the resonator and the qubit. Then, perhaps something more interesting, we can also do a 2-tone qubit spectroscopy experiment in which we are driving the qubit with a continuous tone from its drive line, and then we are also probing the response of the resonator, and which this we can investigate the frequency of the qubit as a function of the flux bias. And we measured, at the optimal operating point, we measured a qubit frequency of about 4.5 gigahertz and an anharmonicity of plus 434 megahertz. That is approximately twice of that of the Transmon. And at the other sweet spot, we measured a significantly higher qubit frequency, but also a much lower anharmonicity. Here in this figure, I'm showing you the results of the qubit spectroscopy experiment together with fits of the theoretical model that I was explaining to you earlier. And you can see that the fits really well, especially around the sweet spots. And also, if we compare the fitted parameter values to the designed values, they agree very well. And this gives us great confidence that our theoretical model is working very well. Here, I'm showing you the anharmonicities of the 5 qubits at the sweet spot as a function of the Josephson energy that has been fitted from qubit spectroscopy. You can see that the anharmonicity is increasing when the Josephson energy approaches the inductive energy, because more and more of the second order potential energy terms are being cancelled and the anharmonicity is thus enhanced. We can also see that the measured anharmonicities agree quite well with our theoretical model. And we can also see that the anharmonicity of qubits A, B, and C is much higher than the typical anharmonicity of transmers. Then we, of course, wanted to investigate the coherence of the qubits. And first we measured the T1. So here I'm showing you the result for one of the qubits. And at this optimal operating point, we measured a T1 of about 8.5 microseconds. And at the other sweet spot, we measured a T1 of about 4.5 microseconds. And here I'm showing you the T1 measurement results on a semi-logarithmic plot. And you can see that with this semi-logarithmic axis, we have a truly linear decay, which also means that we do not see any evidence of, for example, quasi-particle induced relaxation. Then we also wanted to study what is probably limiting our T1. So we measured the T1 as a function of the frequency of the qubit, and we compared the result against different loss mechanisms. And we were able to explain this trend in our data quite well with a model that incorporated dielectric losses, this dashed yellow line, and also Purcell decay through the readout resonator. And so this suggests that at the optimal operating point, the T1 is probably limited by dielectric losses. Then here are some results of T2 measurement. So here you can see a Ramsey T2 measurement at the sweet spot and T2 echo measurements at both of the sweet spots. And at this optimal operating point, we measured the Ramsey T2 of about 3.1 microsecond and an echo T2 of about 8.9 microsecond. The T2 echo was not quite T1 limited, and this was probably caused by some flux noise still. And then we also wanted to investigate the flux noise density by assuming that the flux noise is caused by a 1/f type noise. And we did this by measuring the T2 echo as a function of the flux around the sweet spot, as you can see in this figure. And from this fit, we extracted the flux noise density of about 15 microflux quanta. And this value is about 1 order of magnitude higher than in state-of-the-art squids, but it is also 1 order of magnitude smaller than in the interesting geometric superinductances that have been studied by Johannes Fink's group. Then we wanted to utilize the high anharmonicity and the reasonable coherence times to implement fast and high fidelity single qubit gates. And we studied this for a variety of gate durations ranging from 13 nanoseconds to 46 nanoseconds. And we measured the fidelity for the idle X90 and Y90 gates using interlead randomized benchmarking. And we observed that the average gate fidelity reached 99.9% for a 13 nanosecond gate duration, and the gate fidelity was practically coherence limited, as shown by this dashed line. And then we also wanted to study the stability of the single qubit gates. So we studied we did repeated randomized benchmarking experiments in order to measure the gate fidelity over longer periods of time. And we observed that the gate fidelity was stable over 8 hours. And this was mostly caused by the fact that the qubit frequency was stable, and also the T1 and T2 were quite stable over this period of time. We have also done some preliminary experiments on single-shot readout using the Unimon. But so far we have not used any parametric amplifiers, for example, a TUPA or a JPA. So we only have a cryo-hemp in our setup. And despite of this fact, we have managed to reach a readout fidelity of about 89%, as you can see as illustrated in these figures. And it's also good to note that because we have this harmonic confinement in the potential of the Unimon, you should be able to use quite a high power readout pulse without the danger of driving the qubit to unconfined states, which is possible if you are using a transmon qubit. So finally, I want to provide a summary of the results measured for the 5 qubits, and I will not go into much detail here, but what I want to say is that basically the results over the different qubits were consistent, which was very promising. And also like the theoretical model was able to explain the measured characteristics for all of the qubits. So as a summary, I have introduced you to the Unimon. That is a new type of a superconducting qubit that we have developed at IQM. The Unimon has a high anharmonicity as compared to transmons. It's also immune to low frequency charge noise thanks to an inductive shunt. It is well protected against magnetic flux noise by gradiometricity and a flux-insensitive sweet spot. And also the qubit has a very simple structure since it contains only a single Josephson junction and no superinductors. Some future challenges for us that we are working on is to try to reduce the sensitivity to flux noise further and also improve the design and fabrication process in order to enable a higher Q1. And this is something we are currently working on. Then, of course, we also want to try to implement a 2-qubit gate in the future so that we could really scale up the Unimon processor. And in the future, we are quite optimistic about the Unimon, and we expect that our improvements to the design, fabrication, and materials will promote the Unimon to be a candidate for implementing these gate fidelities with a target of 99.99%. And so I would like to thank you for your attention. And as I mentioned at the beginning of my talk, we have a preprint of our paper available in arXiv. So you should really check it out if you got interesting. And also, if you want to work with us at IQM, you should check our webpage for job openings. And I also want to thank all my co-authors. So this was a joint effort from many people, and it has been a great pleasure to be a part of this research. So thank you. Now I will be happy to answer any of your questions.
Thank you very much for the nice talk. Also, it's nice to see Eastern European names in the co-author list. So we don't have any questions in the chat or Q&A. I have a few questions. Why is it called Unimon? Maybe you explain this.
That's a good question. Actually, we initially had a different name, but then we changed it to Unimon. And the reason was that the qubit unites many advantages that you want to have in your qubit. So it comes from the verb unite, and then we have this mon ending that is common in many superconducting qubits.
Okay, I see. And so are these results meaning that IQM is now from now on is betting on the Unimon and leaving transmons behind, or you have like a mixed approach?
So I would say that this is, of course, like we are in early stages of research. So it will take like time before like Unimon becomes mainstream. And until that, we are staying with transmon, I would say.
Okay. And maybe the last question, this is a technical one, I didn't quite get. Do you envision that you will have to tune the system between some idle position when it's protected and a single qubit control position when you can address the qubit, or you don't have to do that?
We don't need to do it. So we can like address it. We can let it idle and address it at a single operating point, and like it's only protected against low frequency charge noise. So it's still like it's sensitive to AC charge. So you can still just drive it similarly to transmons. So it's very easy to control and similar to transmon in that sense.
Thank you very much. Thanks for the nice talk, and also thanks once again to IQM for supporting Quantum Eastern Europe. To the audience, let's meet in the next session. Thank you, Eric. Goodbye.
Thank you. See you.